In this video, we're going to continue our discussion on colligative properties, but this time we're going to talk about it in terms of electrolytic solutions. That is, solutions that break up to multiple parts when dissolved. For example, salt, NaCl, is an ionic compound. When you dissolve it in water, one molecule of salt breaks into two atoms, one sodium and one chlorine. And so we have a way to talk about this, and that's called the Vant-Hoff factor. The Vant-Hoff factor, or I, is the number of parts something will split into when dissolved. Okay? And really, although we can have theoretical values for the Vant-Hoff, so for example, sugar, when we dissolve sugar, one molecule of sugar does not break apart, so the Vant-Hoff for sugar is 1. Sodium chloride, when one molecule of sodium chloride breaks apart, it brings into Na and Cl, so Vant-Hoff is 2. Generally, in real life, it's not quite those whole numbers because ions can reform in solution. But, we're going to use ideal Vant-Hoff factors for this class. Just be aware in real life, NaCl is closer to maybe 1.9 or 1.8 because some ions reform NaCl in solution. So here's what I was talking about, Vant-Hoff factor. So non-electrolytes, that is something that does not break apart, I should be 1 and you measure it as 1. NaCl, I is 2, but it's actually 1.9. Magnesium sulfide, 1.3. MgCl, when you break apart MgCl, it forms 1 Mg, 2 Cl, so you expect it to be 3, but it's actually 2.7, and so on and so forth. And when you have ionic solutions next to, that are separated by a membrane, we have ways to talk about these solutions. So imagine that you have red blood cells. You have your plasma, then you have the solution inside your blood cells. Now, if the amount of dissolved particles are the same in each solution, they're isoosmotic. The osmotic pressure is the same, so that's what iso means. However, if one solution has a higher osmotic pressure than the other solution, it is hyperosmotic. For example, let's say that inside the red blood cells, there's less salt than outside the red blood cells. What will happen is that all the water will leave the red blood cells and go in the solution. Your solution is hyperosmotic. The water through osmotic pressure is going to try to normalize that force. The opposite of hyperosmotic is hypoosmotic. So let's assume this time your red blood cells have more salt than the water surrounding them. Then the water surrounding them is hypoosmotic. Water is going to rush from outside your red blood cells to inside, swelling your red blood cells and eventually making them burst. That's it for this video, and I will see you in the next video.